Okay, so we have defined normal curvature as follows for any vector, unit vector the expression, the number, real number, Ku, which is just shape operator at u dot u is called the normal curvature of the surface at the point P along the vector unit vector u. Okay. We also showed that we know that for any unit speed curve alpha with, let's say, alpha 0 equals p and alpha prime equals u, we have this. So u dot product double prime is s of alpha dot alpha prime dot alpha prime. Okay. So this expression is also equal to this gadget where u is an unit normal vector field on M. In other words, an orientation. Okay, so let me draw a picture. Okay, so this is our surface, and we have a normal field, and this is our vector u at the point P, and we wonder how the normal vectors, okay, on the surface changes as we move on this curve at the point P, okay, the instantaneous change at the point P along the vector V. So it's just the directional derivative, nothing else. We have done some computations, and we know that this is equal to the following. If let's say gamma is a plane in R3 passing through the point P and containing containing the vectors u and big U. So it contains both this vector and the vector giving the orientation. Then for the curve, then okay, Ku can be computed as follows. So it is plus or minus 0, where is a parameterization for the intersection curve M intersection with the plane gamma, and this is the curvature of the space curve gamma. This sign is determined accordingly. I mean, if the normal vector of the curve and the surface are the same, then it is plus, otherwise it is negative. We have done some examples last time, right? For example, if you consider cylinder, okay, suppose you are at a point here. If you, for example, cut this cylinder by a plane, so the normal vector here is u, normal vector of the cylinder. It is outward normal, let's say. If I cut this surface with a plane, let's say in this direction, in a vertical direction, so this is my little u, then the curve you will obtain, what is the sigma? Sigma is a line, and for line, of course, the curvature is 0. So for that curve, it is 0. Let's say this is u1, but if you cut this cylinder with a plane perpendicular to the okay, vertical line, so with a horizontal plane, then what you will obtain? You will obtain a circle, right? Intersection is just a circle. Intersection will be a circle. Let's say this is gamma 1, this is gamma 2. And in that case, what will be the curvature? Let's say u2 is this vector, okay, tangent vector. This will be the curvature of the curve, which is it's a circle, so it is 1 over r, r being the radius of the cylinder. But for a circle, the normal binormal of the circle, normal of the circle is inward. But in this case, I choose my normal vector, outward normal. So they are pointing opposite direction. That's why this is negative. Okay. We had done some more examples. Let me also talk about this. Suppose we have a sphere of radius r. If you are at any point, okay, and if you cut this Okay, with a plane, let's say, let me choose this vector. This is my little u. And let's say our unit normal vector is again outward normal. So here I choose this vector on the sphere and the outward normal vector, which is u, and we consider the plane which contains this point and the vector u, little u, and big U. If you cut your plane, your sphere, with a plane, so this is coming out, like this. Maybe I should draw, right? So if you cut it like this, or like this, you will obtain a curve passing through this point, and that curve is of course a circle, and that circle has the center of the origin. Therefore, the radius of this circle is also r. So this is my gamma. Therefore, the normal curvature is again plus or minus the curvature of sigma, not gamma, sigma, and it will be again 1 over r. And again, the normal direction to the circle is inward, but I chose this normal vector for this sphere. Therefore, it is again negative 1 over r. Okay. All right. So this was what we had done last time, basically. Okay, we had this. I talked about umbilic points, right? A point is called umbilic if the normal curvature is constant. Let's say k, a constant for all u in the tangent space at that point. So if this normal curvatures are all the same for all vectors, tangent vectors at a certain point, that point called an umbilic point. Okay. Sphere, for example, the curvature at any point along any direction is equal to minus 1 over r. Therefore, all points of spheres are umbilic, right? All points of a sphere are umbilic. For a cylinder, it is not the case, right? In one direction, curvature was 0. In some other direction, curvatures were negative. So some points are not umbilic. Okay. Here is a theorem. First part is this: if P is a umbilic point of a surface M in R3, then the shape operator, S at P is just a scalar multiplication by K, which is equal to K1 and K2. Remember, K1 and K2 were the extreme values of the normal curvature at the point P, right? K1 was the minimum, K2 was the maximum value. For cylinder, K1 is 0, K2 is no. If I choose outer normal vector, K1 is minus 1 over R, K2 is 0. If it is umbilic, of course, all the curvatures are the same, and the statement is that in that case, the shape operator is just 2 by 2 identity matrix times the scalar K. Okay. Second part, if P is a non-umbilic point, in other words, the extreme values are not the same, then there are exactly two principal directions and these are, and they're orthogonal. Okay. Furthermore, if E1 and E2 are these principal directions, then S E1 is just K1 E1 and S E2 is K2 E2. Okay. Well, maybe as a remark, I can say that the shape operator, I guess, I told you last week that shape operator is a symmetric operator. We will see later also that thing. And therefore, it's a 2 by 2 symmetric operator. Therefore, it is diagonalizable, right? Symmetric matrices are diagonalizable. K1 and K2 are the eigenvalues, and E1 and E2 are the corresponding eigenvectors. And since the operator is symmetric, eigenvectors are perpendicular to each other. Okay. In this case, for example, eigenvalues are 0 and -1, and the corresponding eigenvectors are these orthogonal vectors. One of them is going upward, the other one is the horizontal one. Okay, they are the eigenvectors, and these are the eigenvalues. Okay. Principal directions are the directions along which you obtain principal curvatures. Okay, the maximum and minimum values of the normal curvatures. Along each direction, right, along each direction you have a curvature, normal curvature. As you rotate about this point, you obtain a minimum and maximum value. The minimum value is the curvature called K1. The maximum value is the one K2. They are the principal curvatures, and the directions for those curvatures are principal directions. In this case, there are these two directions. One of them is vertical, the other one is horizontal. Okay. We will see all these in detail, but I just tell you, why we have something like this, why we have orthogonality and so on. Okay. Okay, so it's basically linear algebra. Okay, now let's see the proof. Now, recall that we stated without proof that the shape operator is symmetric. Okay, we didn't prove this, but we stated, meaning that at any point, if you take two unit vectors in the tangent space, so u and w are unit vectors, then we have this. Symmetric means this. Why this corresponds being symmetric? Well, this is an operator from this tangent space to itself, right? Tangent space is a two-dimensional object, two-dimensional vector space. So this is R2, this is another R2. And if I choose a basis for, so this is a copy of R2. And if I choose a basis for R2, in that basis, this will correspond to a matrix, right? So SP will correspond to a matrix. Let's say beta, a basis for TPM. In the basis, this is a matrix, A, B, C, D. And if I choose two vectors, U and V, in, let's say, the coordinates of this vector are U1 and U2. So meaning that U is just U1 times, okay, I didn't tell you what the basis is. Let's say basis is just V1 and V2. Any basis. Does it? Yeah, any basis is, I guess. So this is U1 times okay, V1 U2 times V2. So U1 and U2 are real numbers. V1 and V2 are basis vectors. And let's say W has coordinates W1 and W2, meaning that W is just W1 times U1, W2 times U2. Then you see this corresponds to what? This corresponds as PUW corresponds to what? It corresponds to the following. In this basis, it will correspond to the following. W, which is W1, W2, times SP, which is A, B, C, D, times U1 and U2. And the other one, SPW. U means U1, U2, and then A, B, C, D, and then W1, W2. Okay? In other words, you know, I have so I have this matrix, and this expression, let's say, so in terms of vectors, yeah, so U times, okay, SP W is equal to W times SP times U. Okay, and this forces SP to be symmetric as a matrix. Right? This is true for all UW, right? Nasıl görürüz bunu aslında? Şöyle yapsak mesela. Dur bakayım. Biraz daha detaylı yazmaya çalışıyorum da. So, for example, take U to be so 1, 0. Then SPU is what? A, B, C, D, 1, 0. So this is just A and C, right? AC. Take W. Take W 1, 0 also. So W times SPU is 1, 0 AC, right? So this is just A. SPU, I am sorry. This is just A. What about bir dakika. Bunu 0, 1 alayım. 0, 1. 0, 1 alırsak 0, 1 alırsam yok, burası 1, 0. Pardon, 1, 0. Burayı 0, 1 aldım. Nerede silgi? Okay. Burada tıkanmış şey. Pardon. Okay. So 0, 1. This is 1, 0. This is 0, 1. So this is what? C. If you do it the other way around, however, if U is 0, 1 and W is 1, 0, bir dakika ama yok. Yine aynı U ve şey için yapacağım. Pardon. On the hand, since it is symmetric, so SPUV is equal to SPWU, right? I computed the first one. What about the second one? SPWU. What is this? U vector U is 1, 0, and then the matrix A, B, C at this vector 1, 0, B, and D. So what we get is B. So this implies B equals C. Okay, these are the same. We obtain B equals C. Therefore, the matrix representation of SP in this basis is what? A, B, and then C is again B, and then D. So it's a symmetric matrix. Okay. Well, since it is symmetric, it is diagonalizable with an orthonormal basis. Okay, şurayı sileyim de ondan sonra şey. But don't forget that we haven't proved yet the shape operator is symmetric, but we will prove it soon. Okay. Now, since SP is symmetric, it is diagonalizable with real eigenvalues, right? Eigenvalues are real, and orthogonal eigenvectors. And orthogonal associated eigenvectors. Okay, now let lambda 1, lambda 2 be the eigenvalues, and E1, E2 be the associated eigenvectors. So hence SPE1. So this is the eigenvector associated to the eigenvalue lambda 1, and this is the second eigenvector. with the eigenvalue lambda 2. Okay. By dividing this vector, orthogonal vectors, with their lengths, I may assume that they are unit vectors, right? Replacing EI with EI divided by norm of EI, we may assume that so I just scale these vectors so that they have unit length. We may assume that the basis beta, let's say E1, E2 of TPM is orthonormal. Not just orthogonal, but orthonormal vectors of unit length, okay? So they have unit length. On a cylinder, it is easy to see that, you know, these vectors are orthogonal and so on, right? One of them is this vertical one, the other one is the horizontal one. But this is true for any surface, okay? Take any surface. At any point, there are always two vectors, okay? Along which are perpendicular to each other, and they will correspond to our extreme, so they will correspond to principal curvatures. But along one of them, the curvature will be maximum. Along the other vector, the curvature will be minimum. This is true for any surface. Okay, so that's a remarkable fact, I guess. Okay, what else? All right, now in the tangent space, TPM, write any vector U in the basis E1, E2 orthonormal basis as U equals C1 times E1, no, not C times E1, S times E2. Well, Sn where C is cosine nu and S is sine nu. So, you know, tangent space is a copy of R2, usual plane. And I have a basis E1, E2, and I know that they are orthonormal unit vectors. So I may draw the tangent space like this, okay? This is a correct picture. E1 and E2 are two orthonormal vectors. And so this is TPM. And if I choose any vector here, any vector, is it units? Okay, so let's say unit vector. Any unit vector. I measure this angle, let's say nu, and this vector is then just cosine nu times E1 plus sine nu times E2, right? Okay. So what is then? What is Ku? Well, Ku was this. U dot product SPU. U is just C times E1 plus S times E2. S times U, well, C E1 plus S E2. Okay. How much time? I have still time. Okay. Then, this implies Ku is what? C times E1, S times E2.
Hocam kamerayı değiştirebilir misiniz acaba?
Pardon.
Teşekkürler.
Dot product. So S is a linear operator. SP times this vector will be just C times SP E1 plus S times SP E2. Well, dot product. These were eigenvectors, so this is just lambda 1 times E1 plus S times lambda 2 times E2, right? Lambda 1 and lambda 2 were the eigenvalues, right? And E1 and E2 were the associated eigenvectors. Now you take the dot product, keeping in mind that E1 and E2 are perpendicular. So E1 dot product with E1 is 1, but E1 with dot product E2 is 0. So if you compute the dot product, you will get what? C1 times, no, C times lambda 1, and then E1 dot product E1 plus, efendim? Oh, okay, so this is C squared. All right. And then I have S squared lambda 2 E2 dot product E2. And then I have cross terms, E1 dot product E2, they are just 0, right? And these are 1. So what we get is just C lambda 1 times C squared, or, okay, let me write it this way. C squared times lambda 1. Yok, burada değişken olan C ile S, değil mi? Let me write it this way. Lambda 1 times C squared, lambda 2 times S squared. All right, S and C are just cosine and sine values of the angle nu. So they are numbers between 0 and 1, right? So and we have also what? We know that. Okay, no, we don't know. Without loss of generality, we may assume that these are two real numbers and one of them is larger than the other one, right? I can assume that. If lambda 1 is equal to lambda 2, then this is just what? This is just identity matrix, right? Eigenvalues are the same. Well, then S is just lambda 1 times the identity matrix, right? Well, also, of course, Ku will be just K and Ku will be just lambda 1 times C squared plus S squared, but these are sine and cosine, right? So they add up to 1. Therefore, we get just lambda 1. And this is true for all u, in the tangent space, so that P is an umbilic point. So that P is umbilic. right? Because the curvature, normal curvature at any point is the constant lambda 1. Well, that also means that K1 and K2 are both equal to lambda 1, right? Moreover, the principal curvatures, principal curvatures are both equal to lambda 1, lambda 2. So K1, K2 are equal to lambda 1, lambda 2. If they are not the same, if lambda 1, these eigenvalues are not equal to each other, then the normal curvature is just lambda 1 c squared plus lambda 2 s squared. And s and c are just, right, the cosine and sine values of this angle, where theta is any angle between 0 and 2 pi. So what will be the maximum value of this gadget, right? What will be the maximum value and minimum value? Well, then maximum value will occur when lambda 1 is larger than lambda 2. When c is 1 and s is 0, and minimum value will be obtained when this is 0 and s is 1. So then the maximum and minimum values of Ku are lambda 1 and lambda 2, which corresponds to the vectors lambda 1'i elde etmek için, for lambda to obtain lambda 1, we should have c equals 0. C equals 0 means cosine, no, s is 0. So sine is 0 means cosine is 1. Therefore, the angle should be 0. So the angle is 0, which means the vector is this was E1. So vector is E1, and the other one corresponds to pi over 2, so that the c is 0 and s is 1. So you get the minimal value lambda 2. So the vector is just E2. Değil mi? Maksimum değeri 0'da elde ediyor. Minimum değeri 90 derecede. So this means what? This means okay, let me just Okay. So K1 would be just lambda 1, and E1 is the corresponding eigenvector, and K2, the minimal value, is this one with this eigenvector. So E1 and E2 are the principal directions. K1 and K2 are the principal curvatures. Okay. Şöyle yazayım daha doğrusu. Are the principal curvatures with principal vectors E1 and E2. Okay. All right, let me stop now.